Leetcode 297, serialize and deserialize binary tree. It's a hard problem. It takes some thinking, but comparing to other hard problems might not be the worst. So let's get started. Serialization is the process of converting a data structure or object into a sequence of bits so that it can be stored in a file or memory buffer or transmitted across network connection link to be reconstructed later in the same or another computer environment. Yeah, so just give it a couple seconds or couple minutes maybe of additional explanation. Let's say we have a game where we have some layers, let's say that's or some entities like this, and those entities have certain properties, like let's say they have some position, some x position, let's say 10, and y position, let's say 20, and probably some other properties. And as you play the game, you are changing those properties. Yes, and if you close your game and you reopen it again, you would like to have to preserve the progress that you have made. Yeah, and in order for that to happen, we need to somehow map the state of the game from the way it's organized in code in your application to be stored on a disk in a certain way, and in what way you have to decide what kind of way would be the best, and that process is called serialization. Yeah? So if you want to preserve state, let's say that's just one application of serialization. The other is, as they said, for example, moving objects between computers. So in a game context, if, for example, have a multiplayer and there is one server which is processing all the game states, but input is collected from multiple clients, then they also somehow need to send the state of their games to this one central place. And in order for that to be transmitted, you need to have serialization in place. And when you want to restore it, send it back, then you need to deserialize. And so deserialization is reverse process. And in best, you should not lose any information. And here, for example, on this, we can have, say, some local disk. And one of the formats which is used across the board is JSON and JSON dictionaries, which if we use JSON dictionary, we could use something like this. X, let's say, it's equal to 10, and Y is 20. Yeah. And we could store such JSON dictionary on a disk, or we can send it through network and do many things with it. And the advantage of it is that it can be human readable, but it's not that compact. Yeah, so there are other formats as well. But that's the general idea of serialization and deserialization, and it's a very useful thing, and it's a thing that is used in practice a lot, which is something which is not very common for Leetcode problems. So that's not very abstract. It's even though it's considered hard problem, I think it's useful to think about it for anyone dealing with software engineering. So that was the first part, the introduction about serialization. Then let's read what they have written further. Design an algorithm to serialize and deserialize a binary tree. Yeah. So here we were deserializing and serializing state of our game entity, and now we need to think about binary trees. There is no restriction on how you serialize, how your serialization and deserialization algorithm should work. Yeah, so we have complete freedom. The only thing that we need to ensure that a binary tree can be serialized to string, and this string can be deserialized to the original structure again. Yeah, so if we have, let's say, in our code some kind of tree object, and let's say it like this, and this tree object can get serialize the string text. Serialize, I think like this. And then the only thing that they care about is that when you do deserialize, then you will get the same thing as the original. And of course, this also the comparison operator has to be implemented, but in general, that's what we want. Let's say print success. So that's the main idea, and what's happening inside, that's a black box for now. We will be opening that black box in a second. Yeah, but the idea is that whatever tree is, there is something that happened between the serialization and creation of our tree. We want to be able to serialize it at any point to completely capture the complete state of our tree in a string, and then to be able to deserialize using this string and get the original tree in the same way as we had it. Yeah, and that's it. But that, of course, depends as well on this comparison operator. So we would not have the same exact object in memory, just that the state of both of them will be the same. And the original tree structure clarification, the input/output format is the same as how Leetcode serializes a binary tree. You do not necessarily need to follow this format. Okay, so we will not. So please be creative and come up with a different approach yourself. Yeah. And here is on the right side this G-node structure, which will be used for our input into our serialize method, and we also need to return the same structure here back from deserialize. Yeah, so that's the structure on which we will be operating, which has value data, which is storing, and two references, one to the left node, which could be none, and the other to the right node, which also could be none. Yeah, so it's a binary tree, had at most two children. And here is an example. So let's just disregard this, since it's not the same as this. Here we have some arrays, and here we have objects of 3 nodes, and as output we also have an array which is exactly the same as input, and here we will have a string which is not the same. So let's just copy that to Excalibur, and we will be creating our custom algorithm, since that's what they want from us. 1, 2, 3, 4, 5, like this. And 4. Can make it closer. Let's put it here. Yeah, and now, of course, arrows are the most important part. Every graph and every tree. So let's create some arrows. And now the format that I'm proposing is simply use hash character for missing children. Yes. Which would mean that let's start from top and traverse with DFS. So that will be our algorithm. And not algorithms, just one algorithm, singular. And in the case of this tree, we would go to 1, then 2, then 2 has 2 empty children. Yeah, nothing is here. So here, nothing here, nothing here, nothing here. And we can represent that nothing using the hashes. And then we go to 3. Yeah, that's how DFS works. Go as deep as possible in one direction, then return back go up through a single node and try to go as deep as possible again, and go back, and so on until you reached either something that you were looking for, or you traverse the whole tree, if of course the tree is connected. And from 3 we can go to 5 or 4. Because I already have chosen the direction of left first. So to not confuse you, from 3 we will go to 4, and here 2 hatches, and then 5, 2 hatches. Yeah, and that's the main idea. So we will just traverse the tree with DFS until we go to a node which has no children, or a single child. Then the one that's missing will be converted to a hash, and everywhere else we will just use their values and convert them to strings, and that would be our string. We can separate with commas, as I did here, and from that we can also retrieve the tree back using our Deserialize. So if we just write it in a little bit in detail, then the DFS would work as follows. So the first we get 1, and from here we will be filling up some structure, which we can call, for example, vals or result. And let's move it here. So this is like intro part, and here we will try to run it one by one in more detail and see how really can we create this DFS algorithm to fill up values. So in the end, we will get something like this. So here is the main idea, and now we will discuss implementation in more detail. Well, first, of course, we call DFS1, and we will be updating vals. We will add like 1, and we will call DFS on. We'll create some node. No, sorry, we'll not create nodes. We'll be creating in serialization, in deserialization, and in serialization we will be simply calling the DFS on the left child, so, and first, and then on the right. So DFS 1 left, which is equal to 2, and DFS right, which is equal to 3. Here we will add 2, and we'll call DFS 2 times. This one. Yeah, and here we already have missing children, so none 2 times, and none here as well. Let's move it even more here, and so we have more space. Yes, so here we will get the hashes 2 times, and that's how we go. So from here, go here, here, those are calls for this one, those are for this one, and here. And we call DFS left, which is equal to 4. And DFS right, which is equal to 5. So that's how we proceed. We go inside for each one until we reach none. And that's it. And here we will have exactly the same. Here just the values change. So here will be 4, 4, and 4. And then here 5. And let's zoom out a bit to see everything. And we can copy this part just to see how this algorithm can produce that thing. Yep. So at the very first, we execute from top to bottom. We will add 1. Yeah, that will be the first part. Then we add 2. Then those 2 hashes. Then we go to the 3, 4, 1 hash, and so on and so forth. Yeah. So that's how you can pretty much solve any tree. And this is the complete serialization process. And now this serialization will be simply also using DFS, but in reverse. So to deserialize, let's copy it again. And we will use the output of serialization, well, the input of deserialization. Those will be our tokens. And we will need some index, which will start at 0. And we will be moving one by one and deserializing using DFS as well, and constructing our tree using that structure. We can remove the hashes. 1, 2, 3, and 4. If we just start our DFS at I equals to 0, so I will be our index that will be moving. Each time we take 1 token, we will update I and increment it by 1. So the first token that we have is 1. And we can use it to make node of that value. Yeah? Using this structure, we will be creating objects of that structure. And after we used it, we have to now update I to 1. Just simply incrementing it. And now we have the value, but we also need the left and the right. So how do we do it? We simply fill the left one with there is a next result of DFS, and the right with the next result of DFS as well. And after we did it, we return the node. And here inside, so first we go to the left, because everything is executed in sequence, one by one. Can move it a little bit the bottom, and we will have the next token, which is 2. Now I is equal to 1. Yeah. So we create the next node, and the I is equal now to 2. And we, of course, for that node, need to again code node left DFS with I equals now to 2, and so on. Yes. Let's just iterate till we find that I have to move again till we find first hashes. I will not go through whole process since this tree is a little bit big, but just the first part, so you get the gist of it. And now inside that we have the next token. And that means that we don't have to make any more nodes. We can simply return, but we still need to update I now to 3. Sorry, not hash, but like that. And we need to do it here. So that would be the next one, and the same thing would happen to the right. And here I is equal to 3. And we increment I and we get 4. And then finally we go to the node right and do this exact same thing. Since there are a lot of nodes, it will take some time to write it down one by one. So let's just put some dots here, and in the end we will return the node of the root. Yeah, but that's how it's done. Let's just put some arrows here to maybe make it a little bit more readable. So that's the first step, and we go just from top to bottom and so on. Next one. Let's go on. So put here the line so you see that all belongs to the first call, and then we execute again TFS. So we go one step inside, and those things belong to the next one, and this should be moved a little bit, yeah. And this belongs to this. No, sorry, that was correct. No, I made a mistake. Yeah, like this. Yeah, and here is the inner DFS and so on. Up until always we execute up until we get our hashes, then we can return, and the sequence will continue with the next one until everything terminated at hashes. So that's how we do it, and now we just have to transfer this idea from those drawings to code. So let's open our Leetcode and let's try to think how to do it. So first things first, let's initialize our values. By the end, we will just return like this. Okay, so let's start implementing the DFS part of our algorithm, and it accepts node, of course. And here we have two options: either our node is not valuable, either is a valid node, which is none, yeah, or it's none. And in the case it's none, we simply represent it as hash. Yeah, and otherwise we do vals append convert to string and node point data. No, it's called val, not data. Val. And then we call DFS on node left and DFS on node right. And that's it. And here first we call it on the root. We are getting the root. That's it. And we'll have everything. And this serialization is a little bit more complex. So of course we'll also have some kind of DFS here. And in the end, we'll have root that will return. And here first, we need to get the tokens, and we need to have our index I to move through the tokens. That's the main structure. Have all the elements and not root. We can just simply return DFS, and here we will do some things in a second. But let's start with the tokens. So tokens come from the data. And how do we separate our individual elements? By comma. Yeah? So just split comma, and now we converted input string to the list. And now inside the DFS, we will be retrieving tokens one by one. And the token will be tokens of I and I plus 1. And then there are two options. If the token is equal to hash, what does it mean? We have to return none. And otherwise, we have to create objects of that structure. And so our next node is equal to token, and it has a left subtree, which will be equal to what the next DFS call returns, and right subtree, which will be equal to what the following DFS call will return. And that's it. We also need to terminate if I is greater or equal or greater. Let's start with greater, and we'll just check it in a minute. Then the length of tokens, then also return. Okay. Let's see. That's correct. And cannot assign, maybe meant. Oh yes, you're right. I didn't mean that. Those are properties, not function. You are of course correct. Local variable, so we need to change it to self. So that's also property, and here as well. Wrong answer, expected, and let's what's happening here. String and let's open PyCharm then, and log it in a second. So, there is an option to debug it here, but you need to buy premium. That's why I need to use my own PyCharm for that. See it in a second. 1, 2, 4, and okay. Serialize, deserialize, class codec. And let's do Let's create our tree. Tree left will be equal to 3 nodes. Oh, 3 nodes. And right will be equal to 3. We'll have also 3 node of 4 and 3 node. Let's change it just to make the thing easier for me. Left. This and yeah. And sorry, here we will have now this what the serialize 3. And let's pause here. So the realization looks okay. Here is the result. That means that probably there was a mistake in deserialization. And I think I see it already. Then let's see. This is text, and that's pass. None. And because we didn't return the node. So let's run it here one more time. And the node just 2, 3, 4, and 5. Looks correct. Okay, so it looks like I simply forgot to return not none, but the node, not here in the deserialization. Yeah, that's true. Made sense. So let's run it again, and let's see. It's accepted, and let's submit it. We are somewhere in the middle, and so let's try running it again. A bit better, but not that good. And a bit worse. Yeah. So after 2 runs, we are more or less in the middle. So probably there are some more efficient approaches that maybe don't rely on DFS, but on some other algorithm.